Hello, students. This lesson will wrap up the basic shapes in geometry. Remember, we have two definitions for geometry. Geometry is the measurement of the world, and geometry is a language used to talk about shapes and their relationships. So today we're going to review the 6 most basic shapes. So which shape is undefined and has no dimension, the building block of every other shape in geometry? That's right, it's a point. A point has no definition, it has no size, it has no shape. We draw it like a dot and we label it with a capital letter next to it. So that's point A. What undefined shape has only one dimension? Well, when you put a lot of points next to a point, 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 you start to create a line. So a line is an undefined term with one dimension. Okay, and we learned two different ways to name lines. You can name them with a little cursive letter at the end of the line. You can also choose any 2 points on the line to refer to the line. So if I say, hey, look at line CB, you would know that I'm talking about this line right here. Or if I say look at line M, you would know I'm talking about line M. What happens if we put a line next to a line, 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 next to a line? We start to get a shape with 2 dimensions. And I didn't talk about this one yet. This is called a plane. If you have a line next to a line, next to a line, next to a line, next to a line, you have 2 dimensions. Now you have both length and kind of breadth or width. Okay, this is called a plane. So point, line, and plane. Not an airplane, it's a geometry plane. It's a flat surface. It extends in 2 directions infinitely. There are some relationship words with points. So if I have 3 points that are all in the same line, a word that I can put with that is collinear. We talked about that word a little bit, collinear. That just means together on the same line. So what if 3 points are together on the same plane? What would those be called? Those would be called coplanar. So we can have collinear points and we can have coplanar points. The relationship between points. These are not shape words, they're describing the relationship between this point and this point. Coplanar points are together on the same plane. Most of the shapes you learned when you're little were plane geometry figures. So what we know, a line has 1 dimension. What are the other shapes that we talked about that have 1 dimension? We talked about part of a line. So starting at an end point and going off in 1 direction. This was called a ray. And what about part of a line that has a beginning and an ending point? What do we call that piece of a line? That's right, it's a line segment. You could say segment, often we'll say line segment. The notation for these, if I want to talk about this line, if I want to label it, even if there's 3 points, I only need to choose 2. So this is line QS, or QR or SR or SQ. If I want to label array, let's do R. Well, I already had an R, that's okay. A, Y. Okay. The symbol for array is always going to be an arrow to the right, even if my picture is kind of pointing to the left. That doesn't matter, it's just a symbol. It's always going that way. And then it always starts with the end point. So the first letter has to be where the array is beginning, which is R. And then I can choose either the A or the Y, not both, because that would be overkill. So I'm going to call this Ray RA. Ray RA is the set of points that start at R and continue towards A and go past A forever and ever and ever in one direction, one dimension. Line segments. How do we name those? Those are pretty straightforward to name. We need to know where they start and where they end. So we'll call this J, K. So these are J and K are the names of the points at the ends of the line segments. So the line segment is called line segment J, K. One relationship word that we talked about with shapes with one dimension was opposite rays. So if you have a line and a, well, let's mess with your mind just a little bit. Let's say this is B, point B, and this is T, and this is P. If I said, what's a pair of opposite rays in this figure? You would say, well, I could start at B and I could go off towards T. That would be this shape from B out towards T. And the opposite ray is ray B going off towards P. Notice the arrow goes the same way, even though in the picture it goes different ways. So they both start at B. One goes off towards T and one goes out towards P. So ray BT and ray BP are opposite rays. Kind of fun, lots of vocabulary words because geometry is a language. All right, what shapes have two dimensions? They have both a length and a width. Okay, the first one we said was a plane. Usually we draw it like this parallelogram. We can put a capital letter in the corner like H. H is not a point, it's the name of the plane. So plane H. You might hear people talking about plane figures. Those are all the ones you learned when you were little. Squares, that's a two-dimensional shape. Circles. And all of them can be drawn on a piece of paper or on the ground with a stick. And in a sandy like dirt patch, you could draw these shapes like they did way back in the day. Rectangle is a plane figure. Ooh, what's the one we're going to spend the most time in geometry class talking about? Triangles. That's right. And there's more. But what's the one that we can measure with this thing? Do you remember what this thing is called? Yep, it's a protractor. So, yep, when you take two rays and you put them together with a common endpoint, you get an angle. So there's lots of different types of angles. There's these kind, there's these big wide ones that take a lot, almost half the circle to get across. There's these skinny ones. Why don't you find someone near you and ask them, do you know the 4 different types of angles? All right, what'd you come up with? Did you get the cute little ones that are small to get across? From here to here is not that far. It's not very far around the whole circle. It's only, it's only this much of the whole circle. These are called acute angles. So we could say, this is more vocabulary words, right? More words to describe shapes and their relationships. So there's a ton of angle vocabulary. So we could call this T. So angle T is an acute angle. That's good to know. What other types of angles are there? This one is kind of important. You can see it's like right in the middle on the protractor. Okay, it makes a perfectly right angle. In our world, if you look around wherever you are, you'll see a ton of right angles. There are so many even on your tablets or all the corners of the walls, any piece of paper, it has this kind. Okay. This angle R is a right angle. And we put a little box in the corner to show you how perfectly square it is at that corner. Do you remember the big wide ones? The really fat ones, the ones that open really wide to get from here across to here. It's a long way inside the interior of the angle. Almost all the way around the circle. Actually, no, not quite halfway around the circle, almost halfway around the circle. That one's called obtuse. So we could call it angle O. Angle O is an obtuse angle. Okay. And what about the fourth one? The one that we always forget about is this one. Kind of weird. They're not very useful. We don't talk about them too much. Okay, this is a HIJ. It makes a straight line, so we call it a straight angle. Angle HIJ is a straight angle. It's exactly halfway across the circle. To get from H over to J, kind of in a circular motion, would be 180 degrees. It would be halfway around the circle. Okay, so we say that the measure of angle T, or acute angles, is less than 90. The measure of a right angle is exactly 90. The measure of an obtuse angle is greater than 90, but less than 180. And the measure of a straight angle, HIJ, is exactly 180. There's also angles that are more than 180. They're called reflex angles, but we don't use them in this class. So it would be, let me move this. We could measure all of these. We could put these, figure out how big this is. Have to twist it a little bit. Anyway, if I have an angle right here, something like that, and I don't want to measure in here, I want to measure outside and tell me how many degrees that is, that would be measuring the reflex angle. But we're not worrying about those this time. So what kinds of math problems can we do with numbers? Let's find out. Here's some problems that could be on a test or a quiz. And let's consider what's going on here. Which of the following statements are true? Select all that apply. So we see a number line, essentially, and we see some points on the number line. And then we're just going to go through these one by one and see if it's true or false, because it says select all that apply. So we'll just check one at a time. So it says the length of line segment AB. Line segment AB is right here. Starts at A and it goes to B. That right there. What is the length of that line segment? Well, it says it's -3. So 1, 2, 3. I agree that 3 is part of it, but distance can't be negative. The length is always going to be positive. So that is not correct. Nope. No, because the length has to be positive. Distance is positive. It's the number of steps. I'm not going to take -3 steps anywhere. That doesn't really make sense. I could take 3 steps left or 3 steps right, but that's not negative steps. I'm still taking 3 steps. Now let's see what the heck this is. The distance, D stands for distance. So this weird notation right here is asking if the distance between B and C is equal to BC, which it is. And is that equal to 6 minus 1? And then take the absolute value? Well, let's see. We did have that formula for distance of a line segment. So here's the line segment we're talking about. And if I do 6 minus 1, that's 5. So I'm pretty sure the line segment is 5 long. Okay, is the absolute value of 6 minus 1, that equals 5, right? All that equals 5. So yeah, I think that one's right. The notation's slightly confusing, but it's true. All right, what about this last part? What about AB plus AC equals BC? Let's find out. So from A to B is here. And then we have, so from A to B is here. And then we have from A to C is here. Does that equal from B to C? AB is 3, right? And then how much is AC? AC is 1, 2, 3, 4, 5. So AC is 8. And this is 5. Does 3 plus 8 equal 5? Does 3 plus 8 equal 5? No, that doesn't make any sense. Okay. This is how you do geometry problems. You just kind of stick with it, label things, play with the numbers, and see if it makes any sense. Let's look at the last one. Does AB, so the distance between A and B, which is 3, plus BC, the distance between B and C, which is 5, does 3 plus 5 equal the distance between A and C? Well, from A to C is 8. So does 3 plus 5 equal 8? Yes. This is called the segment addition postulate. This is true. If you have some collinear points like A, B, and C, it's always going to be true that if you add this piece, this segment with the one next to it, you're going to get the total. Okay, that's called the segment addition postulate. The two pieces add up together to the whole segment. All right, let's look at another math problem that we could do in a geometry class. This one is asking us to measure, use the protractor. Again, we're selecting all that apply, and we're trying to see what adds up correctly. So I'm going to look for the measure of angle MLN. I think I'll do it in this color. We'll go from M to L to N. And I'm asking if the inside here is 120 degrees out of a whole circle. Whole circle is 360. Does that look like a third of the circle? If I was going to draw all the way around, this much is half the circle. This is a lot less than 120. So that it just looks wrong. This angle is small. The distance in between here is not that far. So this is a not correct answer. I'm gonna get rid of that. Okay, that is way too small to be 120. No. Let's look at another one. The measure of angle QLP. from Q to L to P. Is that a small angle or a big angle? This one's also acute, right? It's kind of small to get from here across to here. So if there's inside numbers and there's outside numbers. For this one, I'm going to start on the inside numbers. I'm going to go from 0 up to 50. Okay, and that seems right. If I use the outside numbers, then it would tell me that this angle is 130. If I have a choice between 130 and 50 for this problem, which one's the smaller number? It's a really acute angle, so I'm going to choose the small number because it's not that much part of the circle. So this one is correct. It's a acute angle. The number on the protractor says 50, so that looks good to me. Let's look at these last two, see if they're right. We have the measure of angle NLO, from N to L to O. We want to add to that the measure, so this number in here, whatever number that is, we want to add to that the measure of angle OLP, from O to L to P. Okay, and the question is, would those two numbers, this one and this one, add up to the measure of angle NLP? Well, what do you guys think? Would this little piece plus this piece make all the way from there to there? Yep. That is called the angle addition postulate. It says the pieces of the angle will form the whole one. Okay, and I don't need the numbers for that, but I don't know, it looks like 10, 20, 30 for that one, and 10, 20, 30, 40 for that one. So 30 plus 40 is 70. Sure, why not? Okay, the last one, let's take a look at that. I think I'm going to change colors here. We'll do yellow. Is the measure of angle QLP, from Q to L to P. And this is what I do in a geometry class all the time. You're looking at the figures, you're reading, you're marking your figures. Is the measure of angle QLP plus the measure of angle PLO, that's this. How much is that? What do you guys think? Does that look like a right angle? Yes, that's 90. Because when you add those two up, it gets that perfectly straight right up through that number 90 that you can barely read anymore. Okay, is that equal to the measure of angle MLN plus the measure of angle NLO? Is that the other half of the half circle? Yep. So these two add up to 90, and these two add up to 90. So this is also true. They both equal 90, so they are equal to each other. All right, here's another one. Really, that you can see that this is a language, and if you don't know collinear or you don't know what these letters stand for, then geometry gets a little challenging. But if you take it slow, you draw yourself a picture is always a really good strategy. You read it, you reread it, you make your picture match what you're trying to do, then it becomes a lot easier. So it says points A, B, and C are collinear. Remember collinear? Together on the same line. And we know that B lies between A and C. So we have a line, and we have some points on the line. We have A, B, and C. Well, we have A and C, and we have B somewhere in between them. And I think I'm going to spread that out just a bit more. Put B here, C here. And then we also know that to walk from A to C, So it says if AC is 48, so that means if I'm walking to get from A over all the way to C, it's going to take 48 steps. And I also know that from A to B is 2x plus 2. So I can mark my figure by putting a little 2x plus 2 right there. Draw myself a picture of what I'm trying to do. And from B to C is 3x plus 6. I'm going to be a little fancy here. I don't think my picture is that good yet. I'm going to fix my picture a little bit because 3x plus 6, that looks like it's going to be bigger than 2x plus 2. I'm going to adjust here. I'm going to put C a little further out. So it's 48 to get to there. This part from A to B is 2x plus 2 steps. And to get from B to C is 3x plus 6 steps. Okay. The question is, what is BC? Well, it's going to be less than 48, right? You think it's a lot less or a little less? How can we find out? Well, we can do an algebra problem because it's geometry. They want us to keep remembering our algebra. The geometry in this problem says that the segments can add up to the big segment. The two little segments add up to the big segment. So the geometry says that AB plus BC equals AC. That's the geometry. That's the segment addition postulate. Now we trade the geometry out for algebra by substitution. And I get a nice little algebra problem that I can practice solving. So this we have like terms. We have a 2x and a 3x, which together makes a 5x. We have a 2 and a 6, which together makes an 8. Oh, that's so nice. Look, they both have an 8 in them. So I can take the 8 off of both sides. With equations, you can do the same thing on both sides. It's okay. There's a 0 pair right there, so that's why it goes away. And then we have 5x is the same as 40. Divide both sides by 5. 5, 10, 15, 20, 25, 30, 35, 40. So 40 divided by 5 is 8. That is not the answer. We did all that work. In algebra class, we're done. In geometry, we have to go figure out what it is we were trying to do. So what is it that this question is asking us for? It wants to know what is BC. Doesn't care about what x is. We want to find in this picture how many steps is it to get from B to C. Okay, the way to do that is to say, okay, we now know, this is what I want for my answer. We now know what x is. So we're going to take that and substitute it in. So it's going to be 3 times 8 plus 6. Okay, what's 3 times 8? 24, and 24 plus 6 is 30. Okay, now I found it. That's the answer. That's some way that you could show work. And just because I care, I can also do this in my head. 2 times 8 is 16, 17, 18. So this part would be 18, and this part would be 30. It's a nice little way to double check and make sure I didn't make a mistake. 18 and 30 adds up to 48. Cool. All right, last problem. Again, we have some writing, some geometry, some symbols, an M, this thing, and we have to read it, make sense of it, and make a picture for it. So this one says we have a point P in the interior of angle OZQ. Okay, so we have an angle OZQ. We have OZQ. And if the measure of angle OZQ is 125, oh my, this is not big enough. I'm going to erase that and make it fatter. I'm going to make it a bigger, wider angle so it matches my picture better. Okay, OZQ. That looks much more obtuse, much more like 125. If point P is somewhere in here, in between in the interior of angle OZQ, and the measure of angle OZQ is 125. Measure of OZP, well, if I put P here, that's actually too big. This is supposed to be 62. So I'm going to undo that. I'm going to try to make your picture as accurate as you can. It's not always possible, but if you take your time, it's not too bad. So I'm going to put point P about here. P is in the interior of angle OZQ. And I am going to draw the angle from O to Z to P. We know that's 62 degrees, so I can put a little 62 degrees in there. And I know from O to Z to Q, that big wide angle to get from there all the way across to there would take 125 degrees of the circle. And the question is, what's the measure of angle PZQ? What do you think? Yeah, you can just do this little subtraction problem. You can do 125 as the total, and 62 is already taken, and we're trying to find this leftover bit right here. So that's going to be 12 minus 6 is 63. Now, this would be the way to get the answer fast, but it's not really showing, you know, like your geometry knowledge. So if you wanted to really impress someone that you're learning geometry really well, you could write it out this way. You could say the measure of angle OZP plus the measure of angle PZQ is the measure of angle OZQ. Okay. This is the angle addition postulate we just talked about. And OZP we can substitute out for 62. And PZQ is what we're trying to find. So we could call it X, or we could leave it like that. And then OZQ is 125. And then you're doing your algebra problem, which is 62 plus X minus 62 and 125 minus 62. And that gets you the same exact answer we got before, which is 63. Okay, but I almost made a mistake. Are we done? Kind of. We got the answer. What we need to do is we need to state it correctly. It asks us for the measure of angle PZQ. So we need to say that the measure of angle PZQ is 63 degrees. Cool. And you can check just to make sure, is 62 plus 63 125? Yep. Cool. That's it. Be good, do your homework, and goodbye, students.